Okay, so in this video basically we are talking about the example which we solved in the bisection method, but here we will solve this example with this linear interpolation or regular Falsy method. So the idea is same, that we have this function f of x, that is x cube minus 5, and we want to find out the root of this function. So first we need to do the bracketing, and the bracketing will be done based on the sign change of this function. So I will take a range of I will basically take a range of values of this x and see the function value at those nodes, and if the function is changing its value between two nodes, then obviously the root will lie between two nodes. So in this case the function is changing its sign between 1 and 2, so the initial guess or the bracket will be 1 or 2, and in this bracket only our root will lie. So I have taken this as 1 and these are two initial guesses. Now in this linear interpolation method, the XR will be calculated as XU minus FU times XU minus XL upon FU minus FL, and we will calculate the value of XR, and then we will see the function value of f of XL, x of XU and f of XR. Now if the function value at this point XR is having same sign as f of XL, then the XL will be replaced by XR and XU will remain intact. If the function value at XR is having same sign as function value at XU, then XR will replace XU, but XL will remain intact. Now in this case, since the function value of f of XL and f of XR are negative, so basically XR will replace XL in the next iteration. So this XR has come here and XU, and then we will recompute the XR, and then we will check for the sign of f of XR, f of XL and f of XU. And by doing so, after 10 iterations, as we can see that the value of XR is 1.709976, and the function value is very close to the 0. It is minus 3.7 into 10 to the power minus 7. And if we look at the error, then the error between the updated value of XR and the old value of XR is coming out as 2.30 e to the power minus 7, and this is very less. Now if we compare the result with the bisection method, then after 10 iterations the value of XR was as 1.709962, but here after 10 iterations we are more close to the final solution, and that is 1.709976. So this is the example problem solved by a regular Falsy approach. Now one must remember that the necessary condition for this regular Falsy approach is that the function should be monotonically convex or monotonically concave. And one more thing which I want to say, that in this XU value will hardly change, because if we can see in all the iterations the XU value is same. That means we can say that the updated value of XR will be X lower, or let us say we can say the updated value of XR at new step will be the old value of XR minus F naught, or let me write it in a different way. So the new value of XR will be nothing but X naught minus F naught XR old minus X naught upon f of XR old minus f of X naught. So this X naught is the fixed point, and here it will be either XU or XL, whatever we choose. So this can be XU or this can be XL, but the new value of this XR will be calculated like this. So here basically the f of this X0 is XU, so that's why it is same, and XR will be calculated based on this 2 minus f of 2 XR old. So initially the XR old is nothing but, initially we will calculate like this based on the line, but later we will calculate with this iterative formula. So just remember the previous formula which we used. So that formula is that XR is nothing but XU minus FU, XU minus XL upon f of XU minus f of XL. This is XU. So remember this formula to update the value of XR. From the next video onward, we will start the open methods, and the first method in open method will be, Picard iteration, or it is also called fixed point iteration. Thank you.